Continuing our study of thermodynamics, the laws of thermodynamics, we're going to get into a discussion of heat engines and cyclical processes, processes by which you repeat the same sequence or the same number of cycles over and over again. This is lesson number 3. So we're going to need to define this term, a heat engine. And a heat engine takes in energy by heat, converts some of that energy to some other form, such as electrical or mechanical, and then does that again and again and again. A good example might be, for example, a steam engine. Think of an old-fashioned steam engine where you've got this coal car or this car filled with wood, and you're throwing the coal and the wood into the huge engine where it is combusted, and this turns water into steam, which is why the locomotive has to periodically fill up with water at various stations as it travels out west. And that steam is what propels a piston to move up and down in a cylinder to drive the wheels on the tracks to pull the train forward. That's one example. Another example might be your typical power plant. Some power plants, of course, produce electricity without producing any steam. Think of a solar plant or a hydroelectric dam. But lots of power plants need to use coal. Theoretically, you could use wood. Maybe they use oil or natural gas, which is pretty common depending upon the location of the plant and the availability of the fuel. Or you can use a nuclear reactor to generate the heat that will turn the water into steam. And as that steam rapidly expands and moves through the pipes, it goes past the blades of a turbine. Think of one of those pinwheels, those miniature blades that you can blow on, or the wind can blow on, and it turns it. In this case, the steam is turning those blades. And as the blades turn, it's connected by means of a shaft with an electric generator. In the electric generator, it's rotating wires in a magnetic field, and that generates electrical energy. Or you can think of the internal combustion engine of a car that combusts gasoline of some type, and the gasoline produces, in the combustion process, it expands rapidly, and this is what's going to push these pistons in a cylinder. You might have a 4-cylinder, 6-cylinder, 8-cylinder. They can go all the way up to maybe 12 cylinders for gigantic car engines that want to accelerate very rapidly or be very strong. And in any case, that's what enables the automobile or the truck or whatever to do work. So these are all examples requiring a fuel to be combusted, and the net result is pushing a piston back and forth in a cylinder, which is then connected to the drivetrain of the vehicle. So another thing that we want to keep in mind is this equation right here, delta U equals Q plus W. We'll be referring to this periodically. It should always be in the background as you read through this chapter. And we said if delta U goes to 0, in other words, if there is no change in temperature of our system, which would therefore mean that Q equals negative W, we call this an isothermal process. If Q goes to 0, which therefore would mean that the work does the change in temperature, the internal change in temperature, no heat is gained or lost, and yet the temperature changes, we call that an adiabatic process. You can have adiabatic expansion, which is cooling, adiabatic compression of gases, which is a warming process. And then you can also have the situation where your work is 0. No work is done. And if no work is done, then your volume doesn't change of your gas. And that would be an isovolumetric situation where it is the heat that causes a change in internal energy, and the internal energy We're talking here about delta U equaling Q in this case. And this is what produces the change in internal temperature, not the fact that you're doing work on the system. So keep this equation in mind. It's very important to know those vocabulary words. So a heat engine therefore carries some working substance, usually a gas is what we're considering in this chapter, through a cyclic process, which means it goes through cycles. Technically speaking, it mentions down here the internal combustion engine is not a perfect heat engine or a technically theoretical heat engine, because you are expelling an awful lot of your heat through the exhaust process. But in the cyclical process, number one, energy is transferred by heat from a source that's going to be at a higher temperature. Think of the steam being produced in the steam engine. And that steam is going to do work. That's what's going to make the wheels go round, for example, or to operate the machine. And then the energy that is left over and the heat that is no longer efficient to use to drive the engine is expelled to a lower temperature and reservoir. Now, a very helpful diagram to consider a heat engine or to represent it is this diagram right here. So let's spend a minute with this. So in this diagram representing a heat engine, we begin with a hot reservoir. This is where the steam is being produced, and that would be, of course, at a high temperature. That's what this means, T sub H. T being temperature, H being hot. And this heat, Q, which you might remember is MC delta T, as long as we don't have a phase change. It might also involve a phase change in which you have mass times your latent heat of vaporization, likely. It goes into the engine. And this engine then does work. The work, of course, is what's going to make the wheels go around, for example. And then the energy that's left over, the energy that is at a low temperature and not sufficient to drive the engine, has to be exited out the exhaust. Maybe this heat is going to be captured in a reservoir of water, and then the water slowly cools down to the environmental temperature, the temperature of the environment, before it's put back, say, into a river or a lake, or maybe it's exhausted into the air. And so this is our example of a heat engine. And you can imagine we can use certain quantities then, such as the starting temperature and the ending temperature, or the heat coming in versus the heat going out, and the work being produced. We can use these quantities to calculate the efficiency of this heat engine, which you're going to see in just a few minutes. So in this particular engine, the schematic representation of a heat engine, the engine absorbs an awful lot of heat at a high temperature. It does work. And then the excess, the unusable heat, goes into the cold reservoir. Note that negative work is being done on the engine, so that W equals this right here. And we want to remember our convention, that if this is my system, and out here are the surroundings, sometimes called the environment in this book. When we have heat exiting or work exiting, those values are negative. And when we have work being done on the system or heat entering the system, those values are given a positive value. So whether we're talking about heat or about work being done on the system or by the system, we have to pay attention to the correct mathematical sign, either negative or being positive. So the work done by the engine equals the net energy absorbed by the engine. So, in other words, we have to find the difference between the heat coming in and the heat going out. If we measure our heat in joules, not in calories, and we measure our work in joules. We don't need that mechanical equivalent of heat, J, like maybe you've seen in a lab before when Q is in calories. We don't need that. And given the first law of thermodynamics that all energy must be accounted for because energy is neither created nor destroyed, if we have a difference, a delta Q, and between the heat coming in at the high temperature and the heat exiting at the lower temperature, that difference in heat energy must be accounted for. And therefore we say that difference in heat energy must be what is doing work. That's the engine is going to be using that energy to do work so that all your energy is accounted for. Now, in the working substance such as a gas, which is typically what we're thinking about in this chapter, because gases can be compressed and gases can expand, unlike liquids and solids, generally speaking. So the work done by the engine is a cyclical process, which means that as the engine does work, it goes like this, and we're coming around and in this irregular circle. And at some point, the piston is back to where it started from. The volume of the cylinder that is open and receiving the new fuel, air-gas mixture, for example, is ready to go again. And you can see we fluctuate between a high pressure and a low pressure. We go back and forth between these two pressures. If you think of an internal combustion engine, you have your intake, where the gas-air mixture enters the cylinder while the piston is withdrawn. And then you have your compression, where the piston moves down, compressing the air-gas mixture. And then you have your combustion, where a spark plug, for example, in a typical car, will ignite that air-gasoline mixture, which pushes the piston back out again, and then you exhaust the excess stuff, and now you're ready to go back again. So you go from low pressure, you compress it up to high pressure, and then you come back down again over and over and over. And in the process inside your cylinder, you begin up with a cylinder wide open before the piston compresses the gas, and then the piston compresses the air-gas mixture, and now you're at a small volume, and then the explosion pushes the piston back out again, and now you're at a high volume. And as we've said in previous screencasts, the area bounded by your diagram represents the amount of work that is done by this engine in this theoretical cyclical process. So, the work done by the engine in this cyclical process is the area enclosed by the curve. And when you have an irregularly shaped curve like this, you would probably need to use some type of calculus, given if you could know what these particular equations, might be several equations to describe this work. All right, thermal efficiency. Thermal efficiency is going to be, what do you put into the system? You put this system, into the system is your heat at a high temperature. Maybe it's the steam. As a result, coming out of your engine, the engine is able to do work. Now your work, of course, can be defined not just by what the work does, such as force times distance. It can also be represented by the change in the heat coming in minus the heat going out, delta Q. And that change in heat has to be accounted for, and that would be the work. This delta Q would be the work. And therefore, we can calculate the efficiency of the heat engine. And that's work out divided by the amount of heat that you had to put in. You can convert it into a percentage by multiplying by 100%. And this would be the efficiency of your heat engine. We like high efficiencies. That's the goal, to make our engines higher and higher in efficiency. which means in terms of loss, inefficiency, we want that value to go lower and lower. We want to minimize the heat loss and maximize the work being done. So keep in mind that some of these ratios, sometimes we talk about our percentage error. Our percentage error would be heat loss, or the energy that's not doing work for us. Then we have the percentage of the good stuff. The good stuff is what we want. We want high efficiency engines that convert the maximum amount of heat into the mechanical workings of the device. So a heat engine with perfect efficiency would have to convert 100% of the heat energy coming in into work, which means that your Q that is lost would equal 0. And of course, that's never possible. It's impossible to have a 100% efficient machine. Sometimes people call that a perpetual motion machine. No such thing, totally impossible. If you're working at a patent office and somebody submits the designs for a perpetual motion machine, a 100% efficient machine, you can immediately suspect that there's some shenanigans going on or something that's overlooked or a big mistake is being made, because these are impossible. This is an essential component of the second law of thermodynamics, that no systems are 100% efficient, but every system, every engine is going to distribute a little bit of heat at least, or a little bit of matter at least, to the environment. In other words, you're going to have the dissipation of energy or matter excuse me, into the environment. You're going to lose energy to the environment, or you're going to spread your matter out. It's going to be distributed. And of course, low temperature energy and matter that is greatly distributed and each of the particles are way far apart from each other represents energy matter that is not useful, that cannot be put to good work. If we look at this problem, apply the efficiency formula to a heat engine, the mathematics here is easy. Keeping track of the sign is the detail that you don't want to overlook. So if we have a certain amount of energy, 2,000 joules of energy going from a hot reservoir and being transferred to a cold reservoir, you can see that maybe 75% of that energy is going to the cold reservoir, which means the other is what's making the machine do its work. We want to find the thermal efficiency in part A, and then how much work does the engine do in one cycle in part B, and then we want to find the power if this whole thing goes through its cycle in 2.5 seconds. And coming over here, so to find the engine's thermal efficiency, and notice this equation is all at a isovolumetric situation, because we're not talking about a change in internal energy here. And notice that the engine's efficiency, since it's grabbing hold of 25% of the energy to do work, it's 25% efficient. We take the total minus the amount of heat that works its way through the system from the hot to the cold, and it's going to be 25% efficient. And we could say it's therefore 75% inefficient. How much work does this engine do in one cycle? Well, our delta Q then is the difference in the amount of heat coming in minus the amount of heat going out, and that turns out to be about 500 joules of energy. And so finally, when we find the power output, if we remember that work equals force times distance, and this is a 4-cycle engine, And we're doing this in 2.5 seconds. We can calculate the wattage, 800 watts. You're familiar maybe with a 100 watt light bulb, which uses 100 joules of energy per second. Well, this is using 800 joules of energy per second. I wanted to double check on something. Going through 4 cycles. I said that correctly. All right, let's take a look at another problem, analyzing an engine cycle. Here's another one of the PV diagrams, which you need to understand. PV means pressure versus volume. And in this particular engine, you know, we have 3 lines. We go from A to B, and then B to C, and then C back to A again. We have a monatomic gas that is going to be compressed in a cylinder, and that compression takes it from atmospheric pressure, 1 atmosphere, or we could say 100,000 pascals, up into 3 atmospheres. And so we are compressing this gas, and my volume stays at 5. The volume stays at 5 and doesn't change. And then part B, we go from a pressure of 3 down to a pressure of 1, but in the process, my volume goes up by a factor of 3. My volume goes from 5 liters all the way up to 15 liters. And then in the third cycle, the volume is brought back to its original 5 volume capacity from the new 15 volume capacity, and we start this process over again. And of course, finding the amount of work done by this engine would require us to find the area under the curve. And we could estimate that by using the equation for a triangle, and then know that it would be less than that. Or if we knew this equation for that curved line, we would be able to find the integral underneath this curve as the pressure goes from 1 to 3 and the volume goes from 5 to 15 liters. So in any case, finding part A, we're going to use the PV equals inert, ideal gas law. And our pressure is given us in atmospheres, so we need our constant that is expressed in atmospheres to be dimensionally consistent so that the atmospheres cancel. And here we have Kelvin in the denominator, and over here, this Kelvin is in the denominator of the denominator, if you see it right there. And this is in the denominator, so Kelvin cancels out, volume cancels out, and I get an answer of 0.203 moles. And then we can now calculate what the new temperature is going to be, and we're going to be going up to 900 Kelvin in this process. Make sure your temperature is in Kelvin. If you forget and you put temperatures in Celsius, you could get some really weird answers because, of course, the Celsius scale does have temperatures that are less than 0. It gives you negative numbers. Now, find the change in internal energy. And we take this equation, which you've seen before earlier in the chapter, and we're just plugging our numbers in, including the answer from the previous problem. And we see that we're increasing internal energy by 1,520 joules. And no work is being done. We're talking about an isovolumetric system here in part B of the cycle. And so therefore the amount of heat is all going towards a change in internal temperature because no work is being done in an isovolumetric process. And then in part C, we have an isothermal process. There is no change in temperature, delta T equals 0. So the internal energy is going to equal 0. And now we can calculate the work being done. And you saw this equation in the previous screencast. And this term here, this natural log, is a result of doing integral calculus. And we can plug our numbers in and find the work as we go from part B, part C, back to our starting point in our 3-cycle system. And therefore the amount of heat coming and going. Part D, what about the isobaric process? This is the part where the change in pressure is constant. There is no change in pressure, but there is a change in volume. And once again, all the way through here, we are taking equations we've seen before, like this one at the very beginning of the chapter, this one a little bit later on in the chapter. And we're just plugging our numbers in all the way through. And I'll leave the rest of this problem to you. And here, except for this part, find the engine efficiency and the net work being done. And we just were introduced to this equation for finding the efficiency. We calculated the heat coming out versus the heat that we put in. And we see that this engine is 20.7% efficient, which means the rest of the energy has got to be dumped into a low temperature reservoir, which might be the environment. So let's take a look at the remarks. Cyclic processes are lengthy, and you just saw all the different parts of this problem. Notice that the change in internal energy for the cycle is 0, and that the net work done on the environment is identical to the net thermal energy transferred, both as they should be. And of course, all of this is somewhat theoretical because technically speaking, you never end up at exactly the same place that you started with, because the second law, as we develop it in this chapter, means that no engine can be 100% efficient. Now, something that we are really happy for all year long are refrigerators, and something that we're really happy for, especially in the wintertime, are heat pumps, and in the summertime, heat pumps. But we just reverse the heat pump when we want to take heat away from something and cool it down, or when we want to capture heat and pump it someplace because we want to warm it up. Refrigerators and heat pumps. And let's take a look at our diagram here. And now what we're talking about is a big difference. Notice that all my arrows in this figure are going in the opposite direction than they were going in the previous diagram. And so what we're doing now is we are extracting heat from some place that's already cold. In other words, we're going against the gradient. Heat naturally wants to go from hot to cold. It naturally wants to flow in that direction. That's part of the 0th and the first laws of thermodynamics. It's also part of the second law of thermodynamics. As heat is hot, it spreads out, and as it spreads out, it's going to cool down. This is the natural direction, this way. But we're going to do work, and we are going to pump the heat in the opposite direction. We're going to extract it from some place that is cold, and we're going to dump it into some place that is already at a warmer temperature. Now, we can't do that unless we're doing work on it. The work that we're doing is done by something called a compressor on a coolant gas, like some form of Freon, for example. Maybe you've heard of that. And so think of a refrigerator. In a refrigerator, we want to take the little bit of heat that is inside the refrigerator at its cold temperature, and we want to keep it cold. So we need to pump that heat and dump it into the kitchen, where it's going to be at a warmer temperature. And in order to do that, the compressor has got to compress a coolant. So my coolant is under pressure, big pressure down here. The compressor compresses the coolant and turns it into a liquid. And then the liquid goes through, in a sense, is exposed indirectly to the internal workings of your refrigerator or your freezer, for that matter. And the little bit of heat that's in the refrigerator or freezer is absorbed by the coolant, causing it to expand. And as it expands, it is pumped external to the refrigerator or freezer. And maybe you can look into maybe you've seen the back side of a refrigerator or freezer where there's these black tubes, usually painted black. And this expanded Freon then loses its heat to the warmer room, and then we repeat the process. The coolant then is compressed by the compressor, and it goes back into the cold reservoir, where it picks up the little bit of heat that is there, causing the coolant to expand, going from a liquid back to a gas. And then it goes back outside the refrigerator or freezer, and the process goes on and on again. We can do the same thing. Let's try to erase some of this stuff. We can do the same thing with our air conditioning unit in the house. On a hot day, what we're going to do is we're going to have our coolant under pressure inside the house. Let's say we're keeping the house at a comfortable temperature of, say, 75 degrees Fahrenheit or 70 degrees, however cold you like it. We're typically at maybe 75 at our house. And outside, it might be like 90 degrees outside. But what we do is this coolant is pumped into the unit that's in the house, and the blowers around the house are blowing the warmer air of the house across the tubes where the coolant is, causing the coolant to go from the liquid to the gaseous state. And then that is pumped outside to your external air conditioning unit, and that's also where the compressor is. And the heat then is lost, and if you've ever been to an air conditioning unit outside, you can feel the warm air blowing out into the already warmer air of the outside. And then the compressor compresses that coolant back again, and it goes back in the inside to pick up some more heat. Now, a heat pump actually can also operate in the wintertime in the reverse. And so in the wintertime, the way this heat engine is going to work is it's already cold outside, but the heat engine, the heat pump can work in reverse, and it can extract a little bit of heat that's at the colder temperature, causing the coolant to expand. We pump it into the inside of the house where it's warmer than the outside. Let's say it's 20 degrees Fahrenheit outside, and let's say inside we're keeping the house at 76 Fahrenheit, a warmer temperature. So it's extracting the heat from the outside, and the coolant expands. We pump it to the inside, and then the compressor squeezes the heat out of the coolant, so to speak, into the house where the blowers blow it around the house, and then it goes back to the outside to pick up some more heat. So that's kind of what we're talking about with a heat engine, a heat pump that can work in both directions. And we can measure its efficiency, oftentimes called the coefficient of performance, the COP. And depending upon who you buy your air conditioning unit from, or your refrigerator from, or your freezer from, or the air conditioning unit of your car from, or your heat pump from, different companies are going to have different coefficients of performance, and that might affect their price. And you have to decide just how efficient you want to be. You'll pay for greater efficiency, but competition is going to cause the different companies to try to improve the efficiency of their engines to give them a economical leg up on the competition, which is good for you. It's good for the environment, generally speaking. And in any case, this coefficient of performance It has to do with how much work does your compressor have to do. Notice work is in the denominator now. And how much heat can you move one way or the other in the numerator. Notice that the units are going to cancel out because everything is going to be in joules. And this here, your book says that good refrigerant or air conditioner will have a coefficient of performance of 5 or 6. And I don't know, in reality, it might be somewhat less than that. Here you can see the back end of a refrigerator freezer unit. Down here is your compressor, the most expensive thing in the entire device. Oftentimes when your compressor goes, it is not worth the money to replace the compressor. You just get rid of the whole refrigerator. Over here are the coils that are where the compressor is sort of squeezing the heat out of the tubes, out of the coolant that is in the tube, and sending it on, and then sending it back in its cycle. And we can also use groundwater heat pumps where we try to extract heat from water deep underground. And in this problem, apply the coefficient of performance of a refrigerator. So we have a 2-liter container of leftover soup at a temperature of 323 Kelvin. In a refrigerator, and we're going to cool that down because we don't want it to go bad. We're going to save it for later. The density of the soup is going to be greater than 1. The density of water, of course, would be 1.0. And so this is a denser soup, obviously, because it's going to have a broth and maybe some vegetables or potatoes or meat in there. And then the refrigerator cools the soup to 283 Kelvin. And we want to find, and if we're given the coefficient of performance of the refrigerator as being 5, find the energy that is needed. So the first thing we're going to do is, since density is going to equal mass per volume, we're going to solve for the mass of the soup, and we get 2.5 kilograms. And then we're going to put that in for M, and we're going to use our specific heat of the soup, which is in this case a little bit more than the specific heat of water. And here's my change in temperature right there. And so we find the amount of heat. Notice we got to have that negative sign in there because this is heat that is going to be exiting our soup and going into the refrigerator and then being removed from the refrigerator. And this amount of heat is going to be in our numerator. There's my coefficients of performance, so we can find the amount of work that has to be done by the compressor. And then we can convert the amount of heat. And in this particular case, we're converting it into horsepower for some reason. We're not converting it into horsepower, but we are this is the conversion factor for watts to horsepower. So the amount of the horsepower, there it is, the horsepower rating of our compressor is 0.250. And so that converts to 187 watts. And then we can come over here and we can find out how long this would take. And our remarks right here is this example illustrates how cooling different substances requires differing amounts of work due to differences in specific heats. Now this is an interesting question right here. Can you cool down your kitchen by leaving the refrigerator door open so that the refrigerator is not just cooling the refrigerator, but your entire kitchen? Now the problem is the coil in the back of the refrigerator is also inside the kitchen, as is the compressor. So unless your compressor and your coil is located somehow outside of the house, you're going to be producing more heat and you're going to be warming up the kitchen. And it's also going to cost you a lot of money as well. And now maybe you can stand right in front of the refrigerator and feel the cooling effect. but the rest of the kitchen is actually going to be getting warmer. Now, the second law of thermodynamics, we're going to be talking about, I'm going to see how much longer we've got to go here. In the second law of thermodynamics, we're going to get into the principle of entropy. And I think because of the length of the screencast at this point, I'm going to stop here, and we'll pick up this in the next talk.